Okay, so I think it's a pretty good time to start. I'll be finishing the our discussion of non-constant coefficient equations or variable coefficients uh, pretty shortly. I basically have just a couple of examples to do, and then we'll be done with that. So actually, most of today, I think, will be spent on these applications problems. So it's called applications. It's really entirely devoted to mass spring problems. I will get into that probably. I would say I'll finish that entirely on Thursday. Again, I haven't put up any supplemental lectures yet, but when I do that, I will let you know. And some things I may push to supplemental lectures just because I want to talk about a particular topic during the main lecture. So in fact, maybe this second half of this applications bit I'm going to put as a supplemental lecture. So again, I haven't done that yet, so don't think you've missed anything. I'm also going to clean up the YouTube channel so that everything is nice and organized. But anyway, so continuing on with this discussion. And no, I don't get paid by Mountain Dew. I wish I did. If I got paid by Mountain Dew, I'd you know. I mean, I guess technically, when I was a freshman in undergrad, I used all of my. We had these things. If you, depending on your meal plan, you got so many bonus bucks per semester, and they didn't roll over to the next semester. So if you had like 300 bonus bucks, and you were going from say fall to spring semester, then you had to spend them all. And anyway, but I spent all of my bonus bucks on Mountain Dew, and even I didn't always eat, both two meals or whatever I was guaranteed for my meal plan. Didn't always eat both of them in a day, and so if you did eat a meal, you got bonus buck equivalent, like $5, I think. So a lot of times I would use that to buy Mountain Dew. And my roommate and I joked that we spent more on tuition than Mountain Dew, which might have been true. But the point is that, or at least in bonus buck equivalent, because they were kind of expensive if you were using bonus bucks. But anyway, um, so at the time, Mountain Dew had this promo where for a 12 pack, if you tore off the interior, you could register on this website, and you got like 3 points for a 12 pack and 1 point for a 2 liter. And it was 500 points for a regular Xbox, like I'm talking the original Xbox. That was like a Mountain Dew themed Xbox. I think it was 500 points. You got a year subscription to Xbox Live for that 500 Mountain Dew points. And so we accumulated enough Mountain Dew points to get 2 Mountain Dew hoodies, a Mountain Dew mini fridge, a Mountain Dew Xbox, and a year of Xbox Live. So it was thousands of Mountain Dew points. So you can do the math on that and add up how much we had to drink in like a semester and a half. But anyway, how does this work? So remember, maybe I should bring it back. So the type of equation that we're talking about when we are discussing variable coefficients in the second order case looks like this once you've put it in normal form. So if it doesn't look directly like this, you got to put it into standard normal form so that it does look like this. All right, so there's what it looks like. The coefficient functions, of course, can be functions of t. That's the entire purpose of this topic. So anyway, how do I deal with this? As I mentioned last time, in order to deal with this, I need to either be dealing with the case where my coefficient functions are actually just constant functions, so that I can actually solve the homogeneous bit, or I need to be given the homogeneous solution. So this is from last time. From last time, turns out that exactly the same thing is true. Your general solution breaks down as homogeneous part plus particular solution. So here's the homogeneous part, here's the particular solution. The issue, though, is that this homogeneous part is something that I can't find if those coefficient functions are non-constant. I have no general method that we're going to learn in this class for finding those things. So because of that, I have to be given those things in the case that we're actually dealing with variable coefficients. But once I'm given those things, then this works in exactly this way, where the particular solution is found in this way. So note that the only difference in this expression is that instead of having these arbitrary constants, these parameters, I have these variable things, right? These functions of t, hence variation of parameters. I'm essentially saying my particular solution is like this, except I'm allowing those constants to vary, so variation of parameters. Okay, so that's how it works. And it turned out, of course, that there's just a quick recipe that we write out, right? So I look for particular solution of that form. Maybe I'll bring this back. So I look for a particular solution of this form. U sub 1 of t, big Y sub 1 plus U sub 2 times big Y sub 2, where big Y sub 1 and big Y sub 2 are the homogeneous solutions that I'm given, right? So those are the things I'm given. And U sub 1 and U sub 2 are things that I have to find from those. So this is what I have here, right? This is the recipe for doing this. So U sub 1 is minus the integral of big Y sub 2 times f of t. F of t, remember, is the right-hand side always in all of these equations. F of t is what we use for our right-hand side. Okay, so I just have this formula for computing these little U sub 1 and little U sub 2. Okay. So that's how variation of parameters works. So for that reason, what's nice is actually there's not a whole lot to it. I just apply that recipe and I'm done. So I'm going to do one more example of variation of parameters, and then I'm going to introduce a method that is equivalent to variation of parameters that generalizes something that I didn't cover for constant coefficients called Green's functions. And I'm going to mention how it generalizes it even though I didn't cover it, just so that you can see it if you wanted to go back and look at that particular section. But I'll stress that I'm not going to ever ask you to do something using Green's functions, for instance. I'm just going to ask you to solve something, not going to specify a method. So here's an example. I don't like this pen. I'm going to go get another pen. Let's see here. I have a whole wad of pens. Surely in this giant batch of pens, there's one that writes well. Okay, so let's try the blue one. Given, this is okay. Given that t and t squared minus 1 are a fundamental set of solutions. So given that t and t squared minus 1 are a fundamental set of solutions of the associated homogeneous equation, find a general solution of the following equation. So 1 plus t squared times x double prime minus 2t times x prime plus 2x is equal to 1 plus t squared squared e to the t. Okay. So, if I said nothing else, this shows up on an exam, you immediately know that you're going to have to use variation of parameters to do this. One, I mean, you could cheat in a meta way and know that, oh, well, it's giving me to homogeneous solutions here, right? And like, when does it do that? I guess I could be really nice in some of the other problems and give you the associated homogeneous solutions, but for constant coefficient, that's the easiest part, right? So that's not doing you a whole lot of favors. So when you see something like this, you obviously know what it's asking for. Looking at this again, you also obviously know that this is not the form that I should leave this in. So if I want to actually proceed, I need to, everything that we did assumes that this thing has already been put into standard normal form. So I got to do that here. So dividing through by 1 plus t squared, this is x double prime minus 2t over 1 plus t squared x prime plus 2 over 1 plus t squared times x. And that's equal to, this is 1 plus t squared squared, so dividing through by 1 plus t squared, I'm left with just 1 plus t squared e to the t. Okay, so this is the equation I'm looking at. Now, a thing to note here, right? If you're worried that this is going to get really, really nasty because these coefficient functions are not that nice, one thing that you should remember is, as I stressed last time, these coefficient functions actually don't come into this process at all, right? So recall that in order to compute the general solution, I've entirely reduced it down to computing these two integrals. And note that these two integrals only depend on the two homogeneous solutions and the right-hand side. Okay, so those coefficient functions don't come in at all. So the only thing that comes in is here, and actually this is simpler now that we've done this division. Okay, so so this is the thing that we use here. Okay, I could talk about the interval of definition here. 1 plus t squared is always positive, so I actually don't have to worry about this thing at all. So my interval of definition is just all the reals. But anyway, so my homogeneous solution, right? So general solution, as always, this is x of t, which is the homogeneous part plus particular solution. Okay, now because I'm given that these two are a fundamental set of solutions, I know that the homogeneous solution is c sub 1 t plus c sub 2 times t squared minus 1, right? Okay, so that's my homogeneous solution. And I know by variation of parameters that the particular solution I seek looks like this. It's u sub 1 of t times t plus u sub 2 of t times t squared minus 1. All right. Recall that in that formulation, I'm writing off screen. Yep. All right. So in that formulation, this is y sub 1 of t is t, and this is y sub 2 of t. Okay. So y sub 1 of t is t, and y sub 2 of t is t squared minus 1. Okay. So then what is it that I look to do? Well, bringing back these formulas, I look to compute u sub 1 and u sub 2. All right. So in order to do that, I compute the Wronskian of y sub 1 and y sub 2. So first, I compute the Wronskian y sub 1, y sub 2. In general, of course, you know what this is. So this is y sub 1 times y sub 2 prime minus y sub 1 prime times y sub 2. So this is accordingly, since remember y sub 1 is t and y sub 2 is t squared minus 1, y sub 1 is t, y sub 2 prime is 2t, minus y sub 1 prime is 1, y sub 2 is t squared minus 1. So this is 2t squared minus t squared plus 1. And so this is t squared plus 1. You might already be thinking that's going to make things really nice. Okay. All right. Oh, well, I guess I'm calling these y sub 1 and y sub 2. It would make more sense to call them x sub 1 and x sub 2, but okay. So I'm gonna just go ahead and actually, yeah, okay. I'll fix that. Can't stand it. It's x sub 1 and x sub 2. Going back to this reference paper, I'll call this x sub 1 and x sub 2. Okay, there we go. All right. So now to compute u sub 1. So u sub 1 of t, again, not an issue for you since you're going to have access to the notes, but just to remember, u sub 1 gets the minus, and this is minus x sub 2 of t, f of t, over the Wronskian of x sub 1, x sub 2. dt. So this is minus the integral of x sub 2 is t squared minus 1. F of t, let's remember what f of t was. Oh, there. Here's our problem. Here's f of t. Okay. So putting that in our recipe, this is 1 plus t squared e to the t divided by the Wronskian of x of 1, x of 2, but that's t squared plus 1. Oh, look, that's so nice. So nice. Okay, and so what do we get here? This is minus the integral of t squared minus 1 e to the t dt. Okay. How do I do that integral? Well, I have to integrate by parts. At least I have to integrate one of these by parts. So if I want to do this by parts, I just have to remember here, this is some review for you, right? So if I rewrite this, this is minus the integral of t squared e to the t minus e to the t, right, dt. So this is minus the integral of t squared e to the t plus the integral of e to the t, sorry, dt here, plus the integral of e to the t dt. So this is the one that I have to do by parts. This is just e to the t. So what do I get here? I get minus, I'm doing integration by parts. So let's remember, I do integration by parts. I want to make the u thing the thing that gets easier when I differentiate it, and I make dv the thing that I can integrate. So u is t squared, du is 2t, dv is e to the t dt, and v is e to the t. So this is u times v, so that's t squared e to the t, minus the integral of v du. There it is. So that's 2 times t e to the t dt. Okay. Oh, and then I have this extra plus e to the t here. So this is minus t squared e to the t plus 2 times the integral t e to the t dt plus e to the t. Let's just do this in our heads, right? So this is, u is going to be t, v is going to, or dv is going to be e to the t dt. So du is going to be 1, v is going to be e to the t. So what is this? This is minus t squared e to the t plus 2 times u times v. So that's going to be t times e to the t minus the integral of v du, but that's just going to be e to the t. Okay, plus e to the t. Let's simplify all this stuff. So this is minus t squared e to the t plus 2t e to the t minus 2e to the t plus e to the t. So that cancels, and I'm going to be able to factor this. How is this going to factor? This is going to factor as, well, okay, maybe I'll just write it out. So this is e to the t times what is left here. So this is 1. This is minus t squared plus 2t minus 1. So what is that? That is minus t minus 1 squared e to the t. Yep. Cool. All right. Okay. So that is our u sub 1 of t is this thing. All right. So let's compute u sub 2 of t. So u sub 2 of t is the integral of x sub 1 of t f of t over the Wronskian of x sub 1, x sub 2 dt. So x sub 1 here was t. So this is t times 1 plus t squared e to the t over t squared plus 1. So those cancel. And I'm left with the integral of t e to the t dt. Again, I can do this by parts, but I know what this is. So this is t e to the t minus e to the t, or t minus 1 e to the t. Right? So the general solution is x of t, which is homogeneous part plus particular solution. So the homogeneous part, as you recall, going back to the first, there it is. So this is c sub 1 t plus c sub 2 t squared minus 1 plus the particular solution, which is u sub 1 of t times t plus u sub 2 of t times t squared minus 1. So recalling what those were from the computation we did, so this is c sub 1 t plus c sub 2 t squared minus 1 plus we found u sub 1 to be minus t minus 1 squared e to the t. So this is this should really be a minus, but I'll put it here. So this is minus t minus 1 squared e to the t times t plus here u sub 2 is t minus 1 e to the t times t squared minus 1. And that's not the prettiest way of writing that, but that will work. Okay. Okay. Let me see what kind of questions we have. Do I have any idea when the exam MATLAB assignment will be? So your midterm will probably be, and I'll probably post it in another week. Is when I'll post your midterm, and you'll have a few days to do it. The first MATLAB will be posted, I should say your next MATLAB assignment will be posted this week. So the end of this week, I'll post your second MATLAB. Okay. All right. So this is our second fully worked example to variation of parameters. This is pretty much all there is to say about it. If you understand how to apply those formulas, then the integrals can be nasty. This one wasn't too bad. We had to use integration by parts a few times, but that's more or less it. That's pretty much how it goes. So anyway, so that's variation of parameters, and that is essentially what you're pigeonholed into having to do because there's just nothing else to be done in those kinds of problems. So one more thing I'm going to do that might seem at first like it is a different approach, but it's not. It's also just variation of parameters, but it's disguised in a particular way, and it's called Green's functions. Now, since this really is just variation of parameters, you might say, what's the purpose of it? There's a lot of reasons why thinking of it from the approach of a Green's function, there's a lot of conceptual things that are very nice about Green's functions. So there's a whole theory about Green's functions that's really, really beautiful, but we're not going to get into that. So again, suppose that I have the following second order equation. I'm not going to do variation of parameters or Green's function stuff for higher order stuff, even though you can do that. So let's say that we have this equation. So then what is the Green's function method? So as always, general solution. I know you're almost certainly sick of seeing this by now. So homogeneous plus particular solution. Okay. Now, the homogeneous solution is still going to have to be given to you in the same way. There's no magic here. We're not going to learn a general method that's going to allow us to solve a homogeneous problem associated to this. So you're out of luck. in that regard. Now, for Green's function, so Green's function method, we seek a particular solution of the form given as follows. So our particular solution is given as an integral from some t sub I, that's some initial time, it's typically not very important, to t of big G of t and s. So G depends on parameters t and s times f of s ds. So a couple of things here. S is a dummy variable that we're integrating with respect to here. So when you're plugging in t values here, right, it's getting plugged into, well, this expression in G and this upper limit of integration. Okay, so that's how this works. Where G of Ts is the following. This is y sub 1 of s times y sub 2 of t minus big Y sub 1 of t times big Y sub 2 of s divided by the Wronskian of big Y sub 1, big Y sub 2 of s. Okay. I can rewrite this in another form. I can rewrite this as the determinant of a matrix. The matrix that this is a determinant of course, is y sub 1 of s, y sub 1 of t, y sub 2 of s, y sub 2 of t, divided by the Wronskian itself as a determinant. And so I can rewrite this as determinant of y sub 1 of s, y sub 1 prime of s, and y sub 2 of s, and y sub 2 prime of s. Okay. This g is called the Green's function. So g is called the Green's function associated to the operator L. Remember, the operator L is just the operator L that, so this left-hand side, we write that as L of T, Y. Right. Okay. All right. So that looks a little weird. Let's see how it works. That's the best way to do it. I'm not even going to go into the theory of why this works. I'm not going to prove anything about these Green's functions. All I'm going to do is a single example so that you'll see, one, how it works. And if you like it, of course, you can definitely use it instead of variation of parameters, although I will caution you that there's no real benefit to doing that because it is variation of parameters, and you'll see exactly how it works out. So let's do the past example. So consider the previous example. And I'm going to go ahead and write it in its nicer form. So x double prime minus, so I'm going to write it in standard normal form automatically. So this was x double prime minus 2t over 1 plus t squared, x prime plus 2 over 1 plus t squared x, and that is equal to 1 plus t squared e to the t. Okay. right, so this was our previous example. So using this example, let's find a particular solution using Green's functions. Okay. Okay. So, according to, oh, I have it on a single sheet. That's convenient. So according to this, to find a particular solution using this, I have this expression going on, right? So how does this all work? Well, just copying directly from that, I seek a particular solution of the form. This is an integral from some initial time to t of g of ts f of s ds. Okay. So in order to see how this works out, obviously I have to compute this g. In order to compute that g, since g of ts is this expression or the determinant of this matrix divided by the Wronskian, I have to compute those expressions. So 1, we had already computed the Wronskian of x sub 1, x sub 2 was, let's go back, I forgot what it was. Oh, 1 plus t squared, that's what it was. So this was t squared plus 1. X sub 1 of t is t, and x sub 2 of t is t squared minus 1, I believe. Let me make sure. Pretty sure that's the case. Yep. Okay. All right. And so my Green's function g of ts is x sub 1 of, so this is, or if you like, it's probably easier to just remember. It's the determinant of, I have x sub 1 of s, x sub 1 of t. I'll write that out. And in this next column, I have x sub 2 of s and x sub 2 of t. And that's divided by the Wronskian with argument s, right? Not t. So this is writing this out. Again, this is the determinant of x sub 1 of s is just s. X sub 1 of t is t. X sub 2 of s is s squared minus 1. X sub 2 of t is t squared minus 1. Divided by the Wronskian is s squared plus 1. Okay. So this is equal to s times t squared minus 1 minus t times s squared minus 1 over s squared plus 1. Okay. Well, don't necessarily see anything nice coming out of that. So we're done here. Okay, that's what our Green's function g of ts is. Okay. All right. So to see how this works out in the same way as variation of parameters that we did for this same problem, going to keep going, right? I take this g and I put it in this integral here. Okay. So choosing my initial time to be 1, you're going to automatically question, like, why did I do this? Why did I choose 1 here? Does it matter so long as the initial time is in the interval of definition? So the point is that it matters in the sense that choosing a different initial time here is going to yield a different particular solution. Okay, but guess what? Well, I'm looking for a particular solution. I don't care which one it is. Okay, so if I choose an initial time that's not 1, what I get in the following is not going to be exactly the same particular solution that I got when I used variation of parameters. But it will still be a particular solution. So does this matter? Not really. The only reason this particular choice matters is because I want it to look as nice as possible. I want it to match the variation of parameters problem or example that I did earlier. So that's why I'm making this choice. Okay, so choosing this initial time to be 1. Okay. And noting that my right-hand side, that forcing function, f of s is 1 plus s squared e to the s, then our particular solution that we're looking for, x sub p of t, is the following. So this is the integral from 1 to t of g sub ts f of s ds. That's just the definition. And that is the integral from 1 to t. This g of ts we found to be s of t squared minus 1 minus t times s squared minus 1 all over s squared plus 1 times 1 plus s squared e to the s ds. Okay, the s squared plus 1 and the 1 plus s squared cancel, so that this becomes nicer. Rewriting this, I get t squared minus 1. I can pull that out of this integral because this integral is with respect to s. So as far as that integral is concerned, t squared minus 1 is constant. So this is t squared minus 1 times the integral from 1 to t of s e to the s ds. Okay, minus t times the integral from 1 to s of s squared minus 1 e to the s ds. Well, what do I have here? My u sub 1 was determined by this integral. This integral is minus the integral of t squared minus 1 e to the t dt. Here I have the integral of s squared minus 1 e to the s ds. So swap s and t, those are exactly the same. But here it's multiplied by this t. Oh, but wait, this is computing u sub 1. And in my formulation of variation of parameters, u sub 1 gets multiplied by x sub 1. But what is x sub 1? T. So this is u sub 1 of t, and this is u sub 2 of t. Okay. That's where these came from. In fact, just quickly note the integral from 1 to t of s e to the s ds. If you actually do that, this is t minus 1 e to the t, and the integral from 1 to t of s squared minus 1 e to the s ds is t minus 1 squared e to the t. Now, these two would not have worked out, as I said before, if we didn't choose this to be 1. If we chose this to be something other than 1, if we chose it to be 2 or 5 or whatever, we would have gotten a slightly different thing here, right? We've gotten a slightly different expression. For our purposes, that doesn't really matter because we're happy with any particular solution, right? The idea of a particular solution is it's any old solution to the differential equation. But I wanted it specifically to match up with the same thing I did with variation of parameters, so that's why. Anyway, that's Green's functions. Quick note is how this relates to Green's functions for constant coefficient. Again, I didn't cover it, but for the interested student, if you look in that section, our big G Green's function is the same as little g Green's function. It's s minus t. Or is it t minus s? Let me think about it for a second. Oh, I guess I think it needs to be t minus s. That's right. So this is t minus s. Don't worry about this here. Looks too bad. Don't worry about this, again, if you're not going to look into this. This is something just extra for those of you that do. Anyway, so that's all I wanted to say about variation of parameters in Green's functions. So in the 15-ish minutes that are left today, I thought I would go over spring problems. Okay. So, how does this work? The name of this section in the online notes is called Applications, or Mechanical Vibrations, I believe is the subtitle. I could be, let me look. Application Mechanical Vibrations, yeah. Which is going to be entirely mass spring problems for us. So oh, he's spring mass is how it's said in the book. That's fine. So what is the idea here? Okay, so the idea is I have something attached to this is a spring, right? So maybe my spring looks something like this. Here's my spring. Attached to that spring, causing that spring to be displaced some amount, is some mass. Okay. All right. So I have a mass. If I didn't attach anything to the spring has like a natural oh, I made it a little bit too long there. That's unfortunate. Let's pretend I didn't do that. Let's say I had it be a little shorter, right? So my spring is a little shorter here, okay, versus me, say, pulling on this mass. Okay, and so I want to come up with a differential equation that in some ways models what happens if I consider this system. So here's some mass attached to spring. So attaching mass to spring, the spring has some resting position. I'm going to call this height. So I'm gonna call this height. We'll say that this is our, if we're using y here, this is our y naught. Okay. The difference between y naught, which is where this initial position the spring is in, versus the position of the spring once I attach the mass to it. This is my y sub r, or resting position. So this is my resting position. Okay, once I've attached the mass, it's not like the resting position of the spring with no mass attached to it. So here's my resting position. So then what I am interested in is the displacement of this from resting position. I'll call that h of t. Of course, in total, there is a y of t distance Okay, that's the overall distance this string has been stretched from initial position with no mass attached to mass attached, and now I have pulled it and I'm letting it go, right? But what I'm actually interested in is this. Okay, so the idea is that I have this setup, I have mass, I do something, right? There are initial conditions. Okay, so at some initial time, something is performed on this system, and this is put into motion in some way, right? H of t is telling me the displacement from the resting position, y sub r, that is, I've already attached the mass, it's sitting there, it's stationary, now I do something to it, right? I pinball it or something, or do something to it at some initial time, and then this h of t is telling me how much it's moved from this resting position. That's what I'm interested in, okay? So, what do I do to model all of this? Okay, so what I do to model this is the following, and I'm going to give the full derivation because some of these relationships that these constants have are important, but I'm going to stress over and over and over again that what is important about these problems is that you look at them and you approach them thinking in your head about the methods that we've used on all the second order equations up till now. And I'm going to stress what it is that's important to remember about these problems, okay? So it turns out that I can model this. So I can model this situation as the following. So I can model this as m y double prime. I'm going to use dots because when they're talking about physical stuff, they use dots. So instead of using prime, I'm going to use dots. That's just to be consistent with the notes. So this is m times y double prime is the sum of the following forces. So I have gravitational force plus spring force plus a damping force. Maybe my spring is like in, some kind of medium that is affecting this, and then an external force. So that's me running over with a baseball bat and whacking the mass, right? Okay, so this is how I can model this, and it's not amazing how you can model it in this way. This is just F equals ma, right? That's all this is. Okay, so this is just forces, mass times acceleration. So this is the sum of all of the possible forces that could be acting on this. So I have gravitational force. Obviously, that's in play if this thing is like dangled from the ceiling or something. I have gravitational force in play. Spring force is the internal force of the spring, right? So depending on how the spring has been made, right, how tightly it's wound, its radius, it's basically what we're going to get into is all of the things involved in Hooke's law, of course. The damping force, again, that's telling you if there's an effect of damping depending on the medium that this spring system is in. And then the external force, which is if someone runs and kicks your spring, right? So all these things, the sum of these is the total force that's acting on this, and then this is the m times acceleration part, right? This is ma. Okay, so that's... It turns out, though, that you're not really going to remember this at all. This is not going to come into it. This is just where all these next quantities come from. And it's important to know that because a lot of these problems involve like a word problem aspect that I know students a lot of times, will find somewhat annoying to interpret. But if you're careful, there's nothing to be alarmed by with any of this stuff. So I'm going to write out what these quantities are. So Before I continue, you'll read in the notes that like pay attention to the units that you're using. I'm not going to do anything where like you having to do unit conversions or something is a thing. I don't care at all about any of that stuff. So everything I do is going to be given to you in the most straightforward way possible when it comes to the units being used. There's no trickery involved with that kind of stuff. Okay, so turns out that this gravitational force with some assumptions, namely uniform gravitational acceleration. My gravitational force is minus mg, where m is the mass in question, right? M is always the mass, and g is the gravitational constant. In your units of choice. Okay. Okay, so we'll say, here we'll use, say, 9.8 meters per second squared. That's good. 32 feet per second squared if you like those sorts of things. Okay, so then the spring force is modeled by Hooke's law. Okay, the reason for introducing these negative signs has to do with orientation and typically reduces the overall number of negative signs that result in the end. You'll see what I mean in a second. So what is this? This is from Hooke's law. Okay, so K is the spring constant. Same spring constant that shows up in Hooke's law. You will sometimes be given K, many times based on the context of the problem. You will have to figure out K from this fact. Okay, so in fact, so note when there is no external force, the mass has a rest position. Y sub r that satisfies zero as this is equal to gravitational force plus spring force at the resting position. So, using this fact and these two relations, what this means is that mg is equal to k times the absolute value y sub r minus y naught. This is the thing to remember. None of this, what I said here, is not important at all. What's important is this. This is very important. Okay. Why is this important? M, you're typically given. Gravitational constant, you always know, right? So there it is. K, you will typically not be given. You'll have to figure it out. But what is this? This is the displacement, right? So note the absolute value of y sub r minus y naught is the amount the mass displaces the spring from its initial position. So that's the displacement. Okay. So typically in the way these problems are stated, you will figure K out from this relationship. Okay. This is used over and over and over again. Okay. All right. So this was the first force we investigated. This is the second one. Let's keep going. So the third is the damping force. And the way that the damping force works is the following. This is minus C times y dot. So the C is called the damping coefficient. Sometimes you will be given the damping coefficient. Typically, you will have to figure it out. How would you figure this out? Usually, if the damping force is not 0, you will be told the absolute value of the damping force at, say, the initial time, okay, at a particular speed. Which would allow you to figure out what this is. Okay, so the damping coefficient is always taken to be non-negative. Okay, so that's how you can determine what C is. Okay, from that. The external force is just some function of T. Okay, the external force is some function of T that is going to vary depending on the context. Okay. Y naught is the resting position of the spring. Okay, that is, imagine you have the spring and you haven't attached a mass to it at all. It's how the spring hangs without a mass attached to it. Say you attach a mass to it and wait for it to stop moving, right? So it's hanging stationary with the mass attached to it. That's Y sub r. That's the resting position. Okay. Okay. So putting all these things together and simplifying, I'm not even going to go through the process because it's not important to remember the derivation. You can look that up in the notes. Putting all these together and simplifying the equation, modeling the amount of displacement from the resting position at a time t, right? H of t, which is displacement from y sub r at time t, is the following. So this is actually m h double dot plus c h dot plus kh is equal to the external force. This is the most important thing to remember in this section, because this is exactly what we're going to study for the rest of the section. So the entire rest of this section centers around this equation. Okay. A couple of things to note about this equation. I'm going to leave this equation on here while I continue to write. So maybe I'll rewrite it here. This is more convenient. Okay, so here's my equation, right? This is all these application problems. Mechanical vibrations are always talking about this All right. So what is the main point of this? So the main thing to remember, I should say, is that at absolute worst, what is absolute worst? So at absolute worst, that means M, C, and K are not zero, and the external forcing function is not identically equal to zero, i.e. it's some function of t there. All right, so this is not homogeneous. So at absolute worst, when m, c, and k are all, well, first of all, m's the mass, it's never going to be zero. But when c and k are not, I can even exclude that because we don't even have to think about that. So when c and k are not zero and the external forcing function is always present, or is also present, it's not zero, this is a second order constant coefficient linear, obviously. So it's a linear second order constant coefficient equation. Okay. That is non-homogeneous. Okay. So the absolute worst thing you get is constant coefficient non-homogeneous. So you're never going to get variable coefficients here, so you're never going to have to use variation of parameters to deal with this. So you would, at absolute worst, you would have to use key identities or undetermined coefficients to find this particular solution. Note, if the external forcing function is identically zero, this is just a homogeneous constant coefficient equation. Okay? Which is like, the easiest thing ever. So the point is that when you think about it, right, like once you set up the problem, you already have all the tools you need in order to solve this. So there's going to be no new solution methods coming from this section. Okay, so you already know everything you need to know to solve all these problems. So main point of all this is if you know how to set up the problems. You already know how to solve them. Okay. And here's the thing. If you're asking, how do I actually set these up in the first place? So setting them up is going to rely on using this relationship to find k, potentially using this relationship to find, typically using this relationship to find c. And once you've done that, you've basically set up the problem. There's not going to be any crazy physics knowledge that's required to set any of this up. If that was required, I wouldn't be able to do it. So in that case, all that you need to know for the most part is actually this relationship here and this damping relationship on the damping force. Those are the main two things you need to know in order to find K and C. So once you know K and C, you're typically given the mass. So once you know the forcing function, if it exists, then you have your problem here. And like I said, at absolute worst, it's a non-homogeneous linear second order constant coefficient equation. You know how to solve those. We already know how to solve those things. So anyway, I'm going to go in depth on some of the cases because they have nice physical interpretations that we'll talk about next time. But that's pretty much it. That's pretty much all I wanted to say. I'll finish mechanical vibration stuff entirely on Thursday, and I will start on Laplace transformations. I haven't uploaded any supplemental lectures yet. I'm going to do that soon because I need to. There's a couple extra lectures I'm going to need. Looking forward at the lecture schedule, a couple extra lectures I'm going to need. Some of the stuff that we were originally going to do is going to be cut out. So most of the stuff that's going to get cut out is going to be from the Chapter 3 material, the linear systems. So I've already spoken with the other instructors of 246. They're doing the same thing so that we're kind of presenting like a uniform, I guess, presentation of 246. So anyway, that's the plan going forward. So anyway, I will see you all. If there's no other questions, I'll see you all on Thursday. And this video, should be all the videos should be up a couple hours after I end. But anyway, yeah, I will see you all on Thursday, and I'll let you guys know when there's going to be supplemental lectures and when I'm assigning your second MATLAB. So anyway, that's it. I will see you all on Thursday.